So in this media, we'll be discussing about LNG propulsion type. Okay, in the market, when you see, we will have different grade of these LNG propulsion available. So we'll see all of them. Just before we move further, we'll read out all these things. So when we speak about this SST, that is superheated steam turbine, we have DFDE, that is dual fuel, tri-fuel, medium speed engine with electric propulsion. So that we have is what is known as is dual fuel, tri-fuel, that is medium speed electric propulsion. Okay, now we have SSDR, that is DRL, slow speed diesel with relic plant. So we have reliquefaction plant, that is relic plant. DFD is high pressure gas injection slow speed diesel, that is MEGI, that is MEGI. We have already covered the difference between MEGI and MEGA in our previous video. Please do watch that video. When we speak about DFD XDF, that is low pressure slow speed diesel engine, XDF 2.0 MEGA, that is gas admission. GTE, that is gas turbine electric. GTE is gas turbine electric. UST is ultra steam turbine. UST is ultra steam turbine. USCT is ultra super critical turbine. USCT is ultra super critical turbine. Cyaringo stays, that is UST plus DFDE. Other hybrid options, that is UST plus GTE. So these nomenclatures are important. We'll be seeing in depth about all these things in our upcoming slides, and we'll be using the short forms for all of them. So please don't get confused. Even if you miss, you can come back in the video and you can refer again. We will not be using the long-term forms in our further discussion. So when we speak about this, that is LNG, so then we have what is known as is boil off gases. So boil off gases, what we use is as consumed as fuel. Now almost very a chunk of boil off gases, even when we have gas ships, their tank construction, we have already covered in a separate video. You can watch that video. So when we speak about this consumed as fuel, these boil off gases, they are consumed as fuel because we have cargo wastage, actually you can say. So that should not go waste. So that is the reason why we are using it. Though the tanks are specially designed to carry at minus 161 degrees centigrade. So these consumed, the boil off gases which is consumed as fuel will be either used by the steam turbine. Then we'll have here is mechanical drive. So here we'll have a steam turbine, conventional, ultra steam turbine. Okay, that is UST. Or we will also have the steam turbine and gas engine, that is stage, STAGE. Okay, steam turbine and gas engine, that is a sort of dual fuel what you are using, but it cannot be dual fuel because here we have steam and the other one is as a gas engine. Now when we are consuming as fuel in dual fuel engine, so it was steam turbine, the case is over. Now when we are using it in as dual fuel engine, either we will have electric drive, that is 4-stroke dual fuel engine, that is diesel fuel diesel electric, DFDE, diesel fuel and diesel electric, or we will have steam turbine and gas engine. Okay, or we'll have dual fuel engine as mechanical drive, 2-stroke dual fuel engine, high pressure and low pressure. Now when we are using it as consumed as fuel, then we have gas turbine, electric drive, combined gas turbine, electric and steam system, that is COGES, combined, your combined gas turbine, electric and steam system. Now when we are using this boil of gases in reliquefaction plant, reliquefied and returned to the tank. So they are again reliquefied, the temperature is brought down through all those systems of compressor and condenser, whatever it is in there. So and then we'll use this as diesel engine, then we have his mechanical drive, then 2-stroke diesel engine. So they are stored in the tank and then we are using it, that is in those tanks only we are doing what is known as your LNG bunkering. So those tanks of bunker also are also specially designed. Okay, now when we speak about this propulsion efficiency, because that is something which is very important to know, when we have these things, why we are using one over the other, and why this market is subsequently and over a period of time it is continuously evolving. So when we speak about this, then we'll take few parameters on which, like, they will set the benchmark for the efficiency factor to be calculated. So those are thermal efficiency of engines and transmission efficiency of components. So that is fuel and that is boil off gas. Okay, so the different steam turbine, DFDE, SSDR, LSDF and COGES, then we speak about. So these things are given. So here you can see that total all these factors you can check over here. So it is almost 40%, COGES 42%, and LSDF is 48%, and then we have HP is 49%. So all this total efficiency you can see in different grades of the engine, and that is the reason the answer lies here, that why market is continuously evolving for different pattern. Okay, now we when you use LNG as a fuel in DFDE engine, IMO tier 3 compliant, MEGI is IMO tier 2 compliant, and then we have XTF, that is IMO tier 3 compliant, COGES is IMO tier 3 compliant, and we have stage is IMO tier 3 compliant. Okay, now when we speak about MGO, that is IMO tier 2 compliant, then we have MEGI is IMO tier 2 compliant, then XTF is IMO tier 2. Now this can be IMO tier 3. So gas oil, that is the reason why now gas fuel, the engine is shifting to gas fuel. Only here you see that MGO, marine gas oil, and this is IMO tier 2 compliant. Now steam turbine 50% HFO plus 50% gas, SSDR is HFO, DFDE is gas, LSDF HP is gas, LSDF LP is gas, COGES is gas. Okay, so tier 3 limit you can see here, that is exhaust emissions in gram kilowatt hour. So that is the tier 3 limit, and that is the tier 2 limit. So you can see here is the blue one indicates the SOx emission, and green one indicates the NOx emission. So you will have here is maximum SOx emission, NOx emission. Okay, so which is tier 2 compliant. Okay, so when we speak about environmental profile, then you can see NOx, SOx, particulate matter, and then when we speak about engine, that the type of engine, then we have XTF, MEGI, diesel, HFO. They are too much. All these particulate matter, SOx, NOx, everything is in high. When we speak about gas injection engine, then here you can see NOx emission is way beyond, and SOx emission is relatively lower, and then particulate matter is higher. But in XTF engine we have all these things in a very controlled manner. Now when we speak about we'll see the difference between all the engine based on the parameters of environmental compliance, thermal efficiency, fuel system reliability and OPEX. Now when we speak about steam plant, that is meets tier 3 gas mode, SCR required for tier 3 fuel oil mode, high CO2 emission, the efficiency is 0.3, so to that will reaches to 0.41. okay, now fuel mode gas only, dual fuel, any ratio, fuel oil only, and then high low redundancy, low high fuel costs. Now when we speak about this DFD meets tier 3 gas mode, SCR for tier 3 fuel oil mode, and then it will be 0.42. Two modes fuel only, gas mode minimum load 10% plus 1%, that is pilot fuel. So 1% we are using is pilot fuel at 10% of on load on engine. Greater steam plant, high redundancy, okay, high engine maintenance cost. Now for this engine when we speak about that EGR or SCR for tier 3 fuel oil mode, scrubber or low sulfur fuel for SECA region, SECA region. Okay, now here it will be 0.47, no gas burning minimum load 10% plus 3.5% pilot fuel. So here pilot fuel increases. greater steam plant propulsion redundancy, high engine maintenance cost. So in this engine we have maintenance cost as higher. So now in this engine, when we speak about an EGR required for tier 3, low CO2 emission 0.51, and then fuel oil only, MDU HFO, gas shear mode, unknown propulsion redundancy, high engine and compressors maintenance cost. So here engine and compressor both maintenance cost will increase. In this type of engine we have is tier 3 gas mode or MDO, efficiency 0.41, fuel oil only, MDO, gas burning, okay, not proven for LNG carrier, DFDE, and then we have greater DFDE, greater than DFDE operational cost, and then we have less than what is known as steam plant. So it lies somewhere in between, but it is not proven for LNG carrier, so that we have to keep in mind. Now you can see here there is the cargo tank, then we have what is known as your boil off gases. Those are coming because ultimately over a period of time we cannot have a tank which is 100% insulated. Okay, we can increase the efficiency, but there is nothing called 100% in this nature. You cannot develop. So because of which, because of there is a break in the insulation, so that is the reason why we have boil off gases, and then that passes through this boil off gas compressor, and then ultimately it goes to the boiler. We also have HFO tank, wherein you can see this as a pilot fuel tank or MDO tank. Now this, see this yellow line, they are going to the boiler, and as well as they are going to the diesel generator. Now from here, so this is a typical steam turbine, okay, HP steam turbine. So from the boiler, now we are running the boiler. From the boiler the steam is generated. Now we have two boilers because the ship is main propulsion is steam driven. So we have two boilers, that may be high pressure boiler or medium pressure, it can be, or medium pressure that will range up to 16 kg. Now from here this green line indicates the steam line, so it will go to the steam turbine. Okay, now it will go to the steam turbine, and then from here you will see it that, and here also it is going to the dump condenser. You can see whatever is the return that will go, and then it will come to the HP turbine, and this HP turbine will ultimately through the reduction gear it will rotate, and then through the reduction gear it will turn the propeller. Okay, so this is all together what we have is known as, so here we will have this electric. So from here this is going to the load, and all this boil off gas compressor is running from this generator. Okay, I hope this diagram is clear for you. This is a basic diagram. Now the same way you see marine boiler, then we have superheated, then we here you see superheater, and then we have the main boiler. This is going to the main turbine, that is HP. Okay, and then we also have here what is known as your LP turbine. We also, after this return goes to the reheat, so reheater, and then again it will go to the IP, and then again it goes to the LP, that is low pressure. Okay, they are driven, and then what, through all these things, reduction gear, okay, through it will be driving the propeller. So here what is new component is added is reheater to maximize your efficiency. Okay, now SST, UST and USCT, when we speak about their efficiency, you can see here lies between 27 to 31%, steam pressure 60 bar, 515 degree centigrade steam temperature. UST is 40 to 45 degree, 100 bar, 560 degree temperature we will have. USCT is 45 to 48, 300 bar, 650 degree centigrade. And then what we have is in future we'll have this UST, that is 48 to 52%, 350 bar, and then we have steam temperature that is known as, that will go up to 720 degree centigrade. DFDE basic diagram, this is, you have GC, U is gas combustion unit, okay, and then forced vaporized LNG and on boil off gases, and then your forced vaporized LNG through the turbine, it will go number 1 engine, number 2, okay. MDO plant, we have this MDO pilot and backup fuel, HFO backup fuel, and MDO is the pilot fuel. If in case we don't have MDO, we can also inject HFO. So now they are going to all these, and then you can see here it's like electric propulsion. So here you can see here through it will go into the, it will rotate the propeller, and through here only it's like a bus bar. So here we'll have accommodation load, cargo pumps, LD compressors. Okay, so basic diagram. So I hope it is clear for you. You can have a look. TFD, compression of air and gas. So TFD, you will have compression of electric, we saw. Now this gas injection, air and gas intake. Air and gas, you can see while in the piston is coming down, air and gas is getting intake, so the valve is opening and is right. And now the compression of air and gases. Now while the compression of air and gases, the valves are shut, inlet and exhaust ports are shut. Okay, ignition by pilot fuel. So at that time, you can see here when the piston reaches just before the TDC, then you have what is known as ignition by pilot fuel. Pilot fuel is injected. Now stage that we had saw LNG, MGO, dual fuel engine, electric generator. Okay, dual fuel engine, and then we have electric generator. So see here we have cargo tanks. Now the boil of gases that will come out from the cargo tank, and we have compressors. Okay, boiler fuel gas compressor and DFE fuel gas compressor. So it will go to the gas heater. After the compressor, it will go to the gas heater. From here it will go to the, you can see here, this will also go to the generator set, and from we will also have pilot fuel, that sorry, this fuel line that is coming, MGO, marine gas oil, is going to the generator, and then from here it will generate through the alternator, it's going to the main switchboard, and you can see here, and this is also supplying the electric power here. Now other line, when we speak about from this gas heater, it is going to through the pressure control valve, and we also have MGO line, please remember it, red line. Through the pressure control valve, it is going to the boiler. Okay, then you also have reheater. From the boiler we also have reheater, it is going to the HP turbine. We already saw this block diagram. Is going to the HP turbine, and from this HP turbine it is going to the reheater, and from the reheater it is coming out and it is going to the IP turbine, and from the IP turbine it is going to the LP turbine, and now this LP turbine is rotating, and then what we have is through the reduction gear, now it is rotating the FPP, fixed pitch propeller, FPP, and you know that we have CPP also, controllable pitch propeller. Here through this electric we have is coming, and then converter, through the converter and transducer and converters, and it is, you can see, through the reduction gear again it is rotating the another set of propeller. Okay, so this is electric propulsion. And then we have what is here is high efficiency reheat UST. You can have a look at this diagram. So it's a basic diagram, it's very simple. If I may have missed something, so please you can comment. So gas turbine electric, when we speak about, same way, same thing, you can just have a look at the diagram. I'll just pause for a while. You can see here. Okay, we'll move further. Slow speed diesel propulsion. When we speak about slow speed diesel propulsion, so then we have a liquefaction plant 2 into 100% when they are running a non-boil of gases, and then we have LNG. Then this we also have this HFO, which will get generator set. We have 4 to 5 units of generator. Okay, and now this will go to engine room 1 and engine number 2, and through this engine it is rotating the propeller. So here you will have propulsion through the engine. Okay, MEGI, when we speak about, that is gas injection. I have already made a separate video on difference between MEGI and MEGA. You can watch that video on MEGI and MEGA. Also, just for your knowledge, this MEGI and MEGA, please watch, because that is a separate question. Okay, now these are the generators. Okay, they are rotating at 720 rpm, high pressure gas handling system. You can see LNG stored at -162 degrees centigrade, compressor 2 into high pressure pump and evaporators plus others, HP system, you can see here, and all these things. The gas valve unit we have here is known as gas valve. So LP is coming here, and then high pressure system is going to the main engine. You can see here HP system, it is going to the main engine, and through the LP here you have is EGR, what is known as for both the engine exhaust gas recirculation. Okay, so then it will become tier 3 compliant. So that is also a difference between gas admission and gas injection engine. It is not tier 3 compliant without EGR. Okay, so that is the difference. When we speak about XDF, you see here low pressure compressor plus low pressure pumps, LNG, and then fuel gas handling system. Through it will go to the gas valve unit, and it will go to the generators, and then it will go to the gas valve unit, and through it will go to the main engine, and from where it is propelling the it is rotating the propellers. Okay, now we go again down. We have XDF auto cycle lean burn. So you know, Ignish, that it is running on auto cycle. So in these types of engine we have two that is ejectors that is there, or we can say the fuel valve, two-stroke DF principle with gas admission and injection. So here you can see pilot injector here. Gas is in gas admission type of engine, you know that gas is admitted just when it is covers the scavenge port. Just when it crosses the scavenge port, gas is admitted. So here the mixing of gases will takes place better as compared to gas injection. In gas injection, just before the TDC, gas is injected, and just before the pilot fuel is injected. Okay, so once the pilot fuel injected, so here you will have better thermal efficiency but higher temperature in case of gas admission. But here in case of gas injection, you will have, it is known as lower this temperature, and because of which NOx emission will be lesser in gas injection, and gas admission your NOx emission will be higher. Okay, now XDF engine. Now see, pilot fuel consumption, when we speak about an XDF engine, is 0.8 gram per kilowatt at 100% power, and 1.8 gram per kilowatt at 30% power. Now high pressure gas engine, we have 0.8 to 5 gram per kilowatt hour at 100% power, and 1.9 to 11 gram per kilowatt hour at 30% power, depending on selected pilot oil energy fraction. Now when we speak about low pressure XDF engine, now you know this XDF nomenclature is by WinGD previously, which was known as Wärtsilä. Now low pressure gas supply means low investment cost for fuel gas supply system, low electric power consumption, and low maintenance cost. Here high pressure gas engine, high pressure gas supply means more expensive fuel gas supply system, compressors and or pumps component etc., higher electrical energy consumption and higher maintenance cost. Now here we have is low pilot fuel quantity ranging from 0.5 to 1% of total energy consumption over engine power. Now here we have is higher pilot fuel quantity ranging from 0.5 to 8% of total energy consumption over engine power. Now in XDF engine can be operated on gas down to 5% power. Start stop is requested in diesel mode. Maneuvering for vessel with CPP could be in gas mode if accepted by class rules. High pressure gas engines can be only be operated when engine power is above 10% in gas mode. Low NOx emission, tier 3 compliant without exhaust gas treatment system. Tier 2 compliant, only an exhaust gas treatment system like EGR or SCR is needed for tier 3 compliant. Particulate matter emissions are significantly reduced compared to diesel engine. Particulate matter emissions still significant. So in this type of engine you can see here. So we have already seen the histogram or in the graph about all the emissions of maybe SOx, NOx, particulate matter in which all engine is we have up to what level. Ultra low NOx emission, that IMO weighted average is greater than 1 gram per kilowatt hour. Low CH4 emission, that is methane emissions, confirmed to be low also in part load operation. Okay, now you can see here is the NOx emission, that is IMO tier 3 cap. IMO tier 3 cap is denoted by this line, and IMO tier 3 average limit is denoted by this line. NOx emission you can see here in this type of engine load percentage at 50%, 75% and at 100%, which is way beyond the IMO limit. And when we speak about methane emission, that is CH4 at engine power, you can see, okay, we have RT flex engine, and then we have 50 DF. You can see here for X62 DF and X72 DF. CH4 emission in the range of 1.5% of gas combustion. Even if considering GHG potential of methane slip, total GHG footprint is positive in comparison to conventional diesel engine. Now, ultra low NOx emissions during 100% of gas operation time. You can see here total tons per year of emission for regular tier 2 and XDF on gas is 150 tons per year. So that is the whole together difference you can see. Okay. Now GHG emission, greenhouse gases emission, CO2 and that is CH4. So MEGI, they are to a tier 2 compliant, you can see here. Okay, CH4 contribution main engine, that is methane is indicated by this your orange color, and then blue color is for that is your CO2 main engine. Okay, the diesel engine is HFO tier 2 set as reference 100%. Engine one diesel engine on MDO tier 2 emits slightly less CO2 due to lower carbon intensity of MDO compared to HFO. Here you can see MDO, this is for HFO which is tier 2, and MDO which is also tier 2, but it emits slightly lesser. Significant reduction in CO2 emissions with gas as a fuel, approximately 25% 30% less compared to HFO. Benefit is partly reduced by CH4 emissions. Now as a net effect, GHG emission of XDF are still 18%, okay, lower compared to a diesel engine on HFO. So diesel engine and HFO, it is little lesser, and then we have reduction of minus 18% for XDF engine which is tier 3 compliant. Okay, now here when we speak about it is solely considering main engine MEGI results in slightly lower GHG emission including auxiliary power for gas compressors and tier 3 compliance of the MEGI. Greenhouse gases emissions of XDF MEGI are typically similar. So here you will have it is typically what is somewhat similar. So these are for the gas greenhouse gas emissions. When we speak about MEGA engine, we have already covered the difference in this video also. I have made a separate video also, the difference between MEGA and MEGI engine. See, scavenging is happening, and now when it is uncovering, gas is admitted. Once it has covered the scavenge port, gas is admitted, and then it reaches TDC. Just before reaches TDC, pilot fuel is injected, okay, and then after the TDC, then you can see just when again started the other stroke, then you will have here is firing which is taking place, that is combustion which takes place. Okay, you can see here LNG cargo tank we have here, LNG supply pump is supplying here, LNG vaporizer, then it is going to 6 bar 16 gas valve unit, and it will go to the engines. Okay, 4 into DF generator set gas valve unit, 2 into this is for 13 bar. At 6 bar it is going for the generator, 13 bar 45 degree it is going for the main. Through the it will go to cargo reliquefaction system, it is going, and it is again coming back, and other the greenhouse gases it is once released after this system only, and then from here only it is the LP compressor is taking the tapping, and through here it is supplying to the gas valve unit, and from the LNG vaporizer it is taking the tapping, and then it will go to the this, or it will directly go from here. Okay, so both the provisions we can bypass the LP compressor, and through the vaporizer we can take it from here at 13 bar 45 degree, we can burn this, okay, in the main engine. Freight rates, you see high, medium steam, low, DFDE low, medium 2 stroke, high. Okay, so equivalent rates in various energy prices scenarios. Okay, so these are there. 672 LNG ships in operation, 323 on order. Global LNG fleet vessel in service by engine type number, you can see all this diagram, which is self-explanatory. I am not going to go in depth of this. Okay, so this is what is all together. So we have already covered all the aspects of the engine based on the research and why others engines are used, low pressure engine, high pressure engine, difference between them, difference between MEGI and MEGA, why electric propulsion and dual fuel, all these aspects we have covered. Stage, okay, XTF, and why MAM BMW nomenclature, and then your WinGD, that previously Wärtsilä, their nomenclature. We have covered all this. I hope it is clear for you, and please, this video is very informative. Please do watch again and again so that it becomes clear for you, and you can post your doubts in the comment section. Thank you so much. Thank you for your valuable time. All the very best for your exam.